In this tutorial we are going to be talking about one of the newest components for Grasshopper that is called TriRemesh, and it comes with Rhino 7.3 or newer version. Using this tool we can convert a Brep or mesh into a mesh that contains triangles with similar side lengths, angles and areas. The TriRemesh component can also generate dual meshes as one of its output that is mainly composed of hexagons and some pentagons and heptagons. Also, I will walk you through each input and show you how we can use in different scenarios. On top of that, you will learn how we can combine features from TriRemesh and MultiPipe component in order to get some really cool results. Without further ado, let's get started. Alright guys, before we start, please make sure you have installed Rhino 7.3 or newer version. Once you install, the TriRemesh component will appear in the Mesh tab Triangulation panel. As I mentioned in the intro of this video, this tool converts Brep or mesh into a mesh with the triangles with a similar side lengths, or the dual mesh with hexagons and some pentagons and heptagons. Now I'm going to show you in the first basic examples how it works. So here we have 6 different Breps or polysurfaces. I'm going to join them into a single Brep using solid union component. And once we have a single Brep, I'm going to place in the geometry. And we can see we get a single mesh with the triangles that are more or less the similar dimension. If I zoom in, you can see it here. If I set true value for the sharp input, the edges of the polysurface will be preserved and it will stay the same as in the input. But if I set false, we will not have sharp edges anymore. Here in the length input, we define the average side length of the triangles. So if I, for example, set to 0.8, we'll get even more precise mesh, but we'll get more triangles, and the computation of this will take longer. As you can see, 2.3 seconds. All right, this is the output of the T or the triangulated mesh. We can also get the output, as I mentioned, the dual mesh. This is the mesh with the NGons or with the hexagons and some heptagons and pentagons. And this is the output. If we want to keep the edges, we can set this to true. And what I really like about this component is that the mesh of each part of the Brep is joined together. So we get continuous mesh all around this single Brep. If you combine TriRemesh component with the MultiPipe, we can get some really cool results. Before I show you how it works, I'm going to set this back to 2. All right, then I'm going to take dual mesh output, extract its boundary, and these curves I'm going to place in the MultiPipe. For the radius I set 0.15, and if I turn this on, we get a single sub-D object which goes all around this dual mesh. I forgot to mention the C output. This is basically the straight edge of the mesh. If I set to false, this output will be empty because we don't have straight edges of the mesh anymore. And if you want to support us on the Patreon, I will show you the trick how we can convert a triangulated mesh using MultiPipe to get a triangulated lattice structure. And this is the output we get. In the next example, I'm going to show you a little bit more complex example. Is how we can create triangulated lattice structure generated from the half of the spheres. Before we start, I'm going to disable the final output, and we'll start from the rectangle. This rectangle will be populated with the 15 points. These guys will be the center of the spheres. The radius of the spheres will be randomly generated within domain, which we define in this part. So I set domain 10.5 to 11.5, and using component random, we'll define a 15 randomly generated numbers within this domain. And once we get the values, we will place in the R input of the sphere. If I turn this on, we get 15 different polysurfaces. Now I want to split all of these spheres on half. We're going to do this generating the plane. So the plane on which the initial rectangle is positioned using component isPlanar. In the P output we get the plane and the component Brep plane. In the intersection tab we can generate the intersection of these spheres and this plane. If I turn this on, we get the intersection curves. Once we have the curves, we are going to use them as cutting shape of the Brep. There is component split Brep, and in the B we'll place the spheres, and in the C we'll place these intersection curves. And on the output here, so each polysurface, it's positioned in a single branch. So for example, these two halves of the sphere, of this sphere, are positioned in the same branch. In the next branch will be positioned these two halves, and so on. Now I'm going to take out only one half of each sphere, and this is what we get. Once we take out these halves, we will use solid union to convert all of these into a single Brep. And once we have single Brep, we'll place in the geometry input of the TriRemesh. If I turn this on, we get triangulated mesh. Depending on what kind of structure we want, either triangulation or the NGons, we can choose here. In the 0 of the stream filter, I will place the triangulation, and in the 1, I will place dual mesh. Then we'll take out its boundaries, and these curves will be placed in the curves input of the MultiPipe. On that way we can create a single sub-D object. If we switch from the triangulation to NGons, we can get this kind of hexagonal lattice structure. In this case, I think it better works if we don't preserve the sharp edges, so I will set to false. And on this way we can create some really cool lattice structure, for example, for some kind of roof. Now I'm going to explain you the input features and what it does. Basically, using this input, we can define which shapes should follow the generation of the mesh. So we have a surface and we have these shapes. Before we place anything in the TriRemesh input, we need to split this initial surface. And we can do this using a split surface component. And splitting curves will be these 4 guys. And in the output we have 5 trimmed surfaces. That's okay. We need to join them in the single Brep. But once we join them, we still have this surface, but also we have these edges inside. That's the difference between the initial one and this one. Once we have this Brep with 4 shapes inside of it, we'll place in the geometry input. And in the features, we'll set these 4 curves. If I turn on the output, we get the mesh. But if I zoom in here, this triangulation of the mesh follows all of these 4 shapes that we place in the features input. And for example, if we want to take out this part inside, we can find the center of each triangle and then check, is the center inside some of these shapes or some of these curves. In the R output, we have 3 different values. 0 if the point is outside of these 4 shapes, 1 if are placed on the shape, and 2 if the point is placed inside the shape. Okay, we just want to find only these points that are inside the shape. Once we have true and false value, we'll place in the cal faces. Basically, if it's true, that face will be removed. That's why I set 2, because for 2 it shows the true if the center of the face is inside the shape. And as I said, if the value is true, that face will be removed. And we have the single mesh as an output with the holes that follow these shapes. Alright, the next example is more complex, and I'm going to teach you how we can combine features input of the TriRemesh with the MultiPipe. This is the initial curve, and we have also some inside shapes. So here we have the shape that are going to be triangulated, and we have 3 inside curves which the triangulation of the mesh should follow. As in the previous example, using curve, we're going to create a surface, and then this surface will be split using split surface. And for the splitting curves, I'm going to use these three curves. Once we have 4 trimmed surfaces, I'm going to join them using Brep join and place in the geometry. For the features input, I'm going to place these 3 curves. If I turn on the output, you can see how the triangulation of the mesh follows these 3 inner curves. Now in the next example, I'm going to divide the mesh. These parts, this one and this one, will be one mesh, and the rest of it, so all of the rest, will be another mesh. We're going to use the same method as in the previous example. We'll take out the center of the triangles using face normals, and once we have the center of each face, I'll place in the point in curves component, and in the C we have these 3 curves. Check the relation between the curves and the center of each face. Using true and false values, we can divide this into 2 different meshes. Here we have mesh faces that are outside of the curves, and I'm going to use the same output, but just on the right click, I'm going to invert the pattern. If I invert the pattern, I will also invert the selection of the mesh faces. Now I'm going to move vertices of this mesh along Z direction. Let me show you first what we want to get, and then I'm going to show you how we can create this. So you can see these vertices are moved along Z direction, but they do not have the same vector amplitude. So that's why I set here random values. I'm going to modify this from 2.5 to, let's say, 3.5. So within this domain, I'm going to generate the same number of values, as many as we have vertices. So this output I'm going to place in the list length, and here we can check we have 198 values. This number will be placed in an input, and we'll have 198 values within domain 2.5 to 3.5. The vector which we'll use to move vertices of the mesh are the mesh normals, and mesh normal will be placed in the V input of the amplitude, and in the A or amplitude will be these values that are being generated here. Okay, so once we have the vector, we'll place in the T input of the move component, and the geometry that we're going to move are mesh vertices, and I'm going to turn on this one. Okay, now we can see all vertices that are moved along normal direction of the mesh face. Okay, we have the points, but how we can create a mesh from it? We can use component construct mesh. For the vertices, we are going to place all these points that are moved along normal vector, and the face are actually the same faces as we have for this input. So we didn't modify the faces. Actually, this is the same face, but just move along normal vector. So we'll place this output from here into an input F for the construct mesh, and that's how we can create the other mesh. All right, so now as we have these 2 meshes, we need to combine them somehow. So the best way to combine these 2 meshes is to take out the edges of this mesh. Actually, we'll take out a naked edge, join them, then find the discontinuity of that curve. Using discontinuity, we'll have all these points, and then these points we're going to project on this mesh, and the projections will be along z vector because we move them along z vector. Once we project them, we're going to use a component line in order to create these lines in between these two meshes. Okay, so we're going to use component mesh edges. In the E1, we have the naked edges of this mesh. We're going to join them. You can see we have the naked edges, and using this continuity, we can extract all these naked points. And now we need to project them on this mesh. For that, we'll take component project point. In the P are the points that we want to project. That points are this one. The direction of the projection will be minus z vector, and in the G, on which geometry we want to project onto is this mesh. Okay, if I turn this on, we have these naked edges projected on the bottom mesh. And once we have these two set of points, we're going to connect them using component line. And in one of the last steps, we are going to take out the phase boundaries of both meshes. We don't need meshes anymore, just need their phase boundaries. And all of these curves, phase boundaries of the top mesh, phase boundaries of the bottom mesh, and also connection line, we'll merge them and place in the single list. Don't forget to flatten it in order to have a single list of curves. These curves will be placed in the curves input of the MultiPipe. For the node size, we'll set 0.15, and the strut size I'll set 0.5 in order to get this more organic look. And this is our final output. If I rotate this a little bit, you can see the final output of this triangulated lattice structure will follow it. Before we continue, I just want to mention the extended version of this tutorial, in which we'll use some of the TriRemesh features to create tensile structure without Kangaroo. You will be able to switch between triangles and NGons as a lattice structure, change its density, thickness, manage its transition from the bottom surface, and how to solve the issue in situations when you can't create MultiPipe from triangulated mesh. This you can watch on our Patreon page and support our work at the same time. On top of that, you will also get access to all our extended tutorials and project files. In the last example, I'm going to show you in what kind of situation target input is really convenient. Using this input, allowing us to create the mesh that will be shrunk and wrapped onto target geometry. So imagine we have a mesh of the cars, but this mesh contains many naked edges. So we want to create a single mesh without naked edges that also will be able for 3D printing. As you may know, the meshes for 3D printing shouldn't contain any naked edges. So we are going to take this mesh and create the bounding box around it. And that bounding box we're going to convert into Brep. So simply just take this output and place in the Brep. Instead of having box, we will have Brep. Because for the geometry input here, we need to place either Brep or mesh. If you place the box, it won't work. So that's why we convert into Brep and place it in the geometry. As a target geometry, we'll plug this mesh of the cars. And as an output, we'll have triangulated mesh without any naked edges. So if I connect it here, you can see in the E1 where the naked edges are positioned, this is empty. So if you want to have even more precise this output, you can set, instead of having 0.2, we can set 0.1. Obviously it will take more time to calculate everything, so with 0.2 it takes 13.5 seconds on my computer, but let's see how much it takes if we place here 0.1. Alright guys, after 1.1 minutes the calculation is finished. So I'm not recommending to set this number really low because it will take a lot of time to compute everything. And what we can do after this, we can add smooth mesh in order to smoothen this a little bit. As you can see, the final output is simplified without any naked edge, and it is 3D printable. Before I wrap this video up, I would like to share something with you. If you're in architecture and you're interested in learning more about Rhino and Grasshopper, but you're tired of searching through thousands of tutorials online and wasting so much time doing that, and you're looking for a structured learning approach with one-on-one support, we created a course called Rhino for Architects that will guide you through all of the basics of both Rhino and Grasshopper. In addition to that, we'll be covering some advanced modeling techniques using sub-D division tools for Rhino 7, which will allow you to create any kind of geometrical shape that you imagine. When it comes to Grasshopper, we'll explain every single essential component with examples and homework files, so even if you're a total beginner, you'll be able to understand the logic and mathematics behind the program. On top of that, we'll teach you all about various plugins for Rhino that are used in architecture, such as V-Ray, Visual Arc, and even Bongo for architectural animation. Lastly, we'll cover architectural presentation, creation of diagrams, and couple of case study projects. If this sounds like something you would like to check out, feel free to schedule your free Zoom call with us in the first link in the description. On this call, we will evaluate your current skill sets, determine if this course can help you out, and on top of that, we will share our learning platform with you so you can get better idea how all of that looks on the inside. Click on the link below the video and we'll talk soon. Take care.